Yeah. So I think it's getting recorded, right?
Yes, it's recording.
Yeah. Yeah, sure. Yeah, so those four questions we have to. So our first question is like the child is running a staircase with 10 steps and can hop either one, two, or three steps at a time. And we have to implement a method to count how many such possible ways the child can run up the stairs.
Mm-hmm. Well,
Yes.
actually, this is the first question.
Yeah.
I think Ayush, he was last time, right? The host. So
Yeah.
he covered this to some extent, seems so, or maybe he covered the Fibonacci series. Yeah, yeah,
It's a
but
kind
what
of same staircase
almost
problem.
correct, it is almost the same. But I
Yeah.
was thinking, okay, if we have this question, right? So
Okay.
if you look at this question in the book, they have some hints also. So, okay, the hints actually they have just marked it with some numbers, and then you have to go and
Numbers.
refers in the hint section.
Yeah.
So yeah, but all of them are not so good. Some of them are really good. I was going through some of them. Sometimes it helps to break down the problem. See, so therefore I thought maybe just read the hints also, and it will help us in methodically, break down the problem, something like
So
that.
we able to post the hint on the share screen.
If you have it, Santosh, since you want to share the screen.
Oh, that's fine. I can read it, some
Yeah,
of
yeah,
the hints because in the book actually you cannot display the book, right?
yeah, exactly. That's
So
the problem. Yeah,
yeah.
Okay, yeah.
So
But for me, I think that those hints, guide me to the right direction.
okay.
Not sure if it majority of them it help.
Right. So I was thinking, what it's no harm trying them, right? I agree what Leon says.
yeah,
Yeah. Sometimes it might work, as well as I was looking for some of the solutions in this book, and the sum of solutions what we have been trying, they are slightly better also, in the lead code. But I would still say that why don't we give a chance to all the solutions what they have been described in the book as it is, because they might
exactly.
be the starting ones, right? Something like
Yeah,
that. So
yes.
okay, just
Or
go through the hints one by one.
even if
Oh,
we not be able to see the hint, if you remember the hint, or you can look up look at the problem, and you can say the hint, then probably it can guide us go to the right direction too.
Right.
yeah, right.
Sure. Okay, so I did something. Okay, so the first hint in this problem, what is said is hint number 152 or something. It says approach this from top to down. Okay, this
Okay.
is what is the very last hop the child made. Okay, and then second it says if we knew the number of paths to each of the steps before step 100, could we compute the number of steps to 100? Okay, and then the third one says we can compute the number of steps to 100 by number of steps to 99, 98, 97, and this corresponds to the child hopping 1, 2, or 3 steps at the end. So do we add those or multiply them? That is if f of 100 equals f of 99 plus f of 98 plus f of 97,
Yeah,
or if it is f of 100 equals to f of 99 into f of 98 into f of 97. So why do we add or why do we multiply, something like that? So what it says, we multiply the values when it is like we do this, then this, and we add them when it's like we do this or this. Whenever we have an ORing, we just add them, and when we have to do each and everything, then we multiply them, right? So that is what is said.
addition and multiplication principle. This is
Right.
yeah,
So because at the end we add them, right? We actually, if we have f of n, we actually add f of n minus 1, f of n minus 2, and f of n minus 3, right? So
Yeah.
that will be the implementation, right? But why we add them and why we don't multiply them? The reason what is said is why we add them, because we want to do, or either to do this or do this or do that, right? Either we take step 1, step 2, or step 3. So therefore we have to add them. Or why we, and when we have to multiply them, if we have to do all of them together, okay? So but in this scenario it's not like that, so we just do one at a time. So that's the
So
only thing.
I think multiplication is like if I have to do first step and then second step also and third step also, right? Then in that case multiplication.
Yeah, if I have to do all of the 3 together.
Okay, yeah. But here either
That
of
is
them
what
you
I
have.
look at it. Yeah, means
Yeah, sure.
yeah, maybe wrong, but
No, looks
that is
like
what
it
is
is.
said. Yeah. And then what is the runtime of this method? And it says like you think carefully, and then can you optimize? Then you try memoization, because just a recursion is an inefficient way of doing it, right?
Yeah, sure.
So these were the few hints what has been said. Okay, so do we want to actually go through the
Hints.
implementation, or?
Yeah, what do you say? Like, I have implementation using recursion and what do you say? Memoization both.
Yeah, actually we can quickly go through, because we don't have to spend more time in that, right?
Yeah,
But
no,
you can actually walk through also, and
sure,
if
sure, sure.
anyone has a question, will come up with that. But
Yeah,
I think out of the hints what has been said over there, the only important hint was like why we have to add or why we don't multiply, right?
multiply. Yeah,
Yeah,
sure.
because the rest of the problem is almost the previous Fibonacci series one, right?
Similar, yeah, definitely. So this is like what I mean. Recursion if steps less than zero. I mean, if x is less than zero, zero. If it is zero, that means one step only you can take, right?
Mm-hmm.
And if x equal to one, I mean, return one. Otherwise, what you say, you can go for all the x minus one plus x minus two plus x minus three, and recursively just
Okay.
do this. Yeah, and this is just like memoizing. I mean, I've created a memo table, and for x greater than one, I mean, for equal to one, you go for this one step you will take. If it is two, then you just sum up the previous two, 0 and 1. And if it is greater than 2, just what do you say, form this loop. I mean, I minus 1, I minus 2 plus I minus 3, and keep it in the memo table.
Mm-hmm. So x is less than 0, you return 0. That is the base case.
Yeah.
And if it is greater than or equal to 1, you return 1. Okay, but why you have that memo 0 equals 1 before that, x greater than 1?
For the zeroth step, if x equal to 0 only, I mean, either you can take 0 step, 1 step, or 3 step, right? No,
Uh-huh.
I think. So for that kind of base case, you can say one more. Like, because when I'll do it for one, I'll need to pick the value. When I'll do it for two, I need to pick the value for zero also, right? For two, I'll have to go for memo of one and memo of zero. So
Okay.
memo of zero, I'm putting as one.
So let's say if x greater than or equal 1, and let's say x equal 5,
Okay.
which is greater than or equal 1, right? Wouldn't that make
Yeah.
memo of 1 memo of what?
Memo of one, yes.
Oh, memo of 1 is equal 1 always. Oh,
Yeah.
this is not like I see.
Okay, but are we not supposed to make return a memo if it is not equal to -1, right? Because you are initializing it to -1, then only you return, right? So, but okay.
Yeah,
I
I think
think yeah, everyone will have a different implementation. Yeah.
I think it would be clear if you check if in a memo first, right?
Uh-huh.
Yeah,
But,
and if it is
but
not,
you always make the assignment to memo 0, memo 1, memo, you know, all the time, or memo 2. Every recursive call, you're gonna make that assignment.
Mm-hmm.
okay,
Okay.
Okay, no problem.
yeah, yeah, sure.
But
So
we
what were you
can.
saying? Like, uh,
No, usually what we do in memoization, we just look for if the value of the memo of that particular is not equal to -1, because you initialize to -1 right there,
yeah,
and then
yeah.
you
Oh, you're
return the
saying
value.
before doing the recursion, right?
Yeah, yeah,
Yeah, yeah. That also I could have done. If memo not equal, I mean, or that place not equal to -1, you return the result. Otherwise, we can run this one.
Hmm.
Yeah, yeah, that.
Okay, so you did the iterative way instead of doing the, okay.
Yeah, yeah, sure.
Because this chapter is completely of recursion and dynamic programming,
Yeah,
so I would prefer to do most of the problems using top down. Uh,
top down. Yeah,
I try to stick to the what book says, all of.
yeah,
Yeah, because it confused to me because in the method, the name of method is like recursive, but
Right,
it's
right, right.
iterative.
yeah,
Correct.
yeah,
Yeah. Okay. So if we
yeah.
move to the second problem, right, the power
Mm.
set or one, what it says, right?
Oh,
I think,
this
yeah,
one.
yeah.
Yeah,
Second problem, write a method to return all the subsets of a set.
yeah.
Correct. So this is also, I think we have been solving this problem, right? In
Lead
lead
code. Yeah,
code. Correct.
yeah.
So some of the hints what have been, in this for this problem, they start with like this. First is how can you build all subset of a sub A, B, C? Like you have a set A, B, C, then how can you build all subsets of this A, B, C from the subsets of A and B? You know, so it's just trying to give a hint, right? It's just like that, a hint. So this is the way you need to think. Like if you want to form a subsets of A, B, C from a subset of A and B, just A, B, how do you do that? So then one way is like anything that is a subset of AB is also a subset of ABC. Which sets are subset of ABC but not of AB, you know? So that comparison is doing that. So subsets that contain C will be subsets of ABC but not AB, right? And
Yeah,
can you build those subsets with the subsets of AB? So it's like when we have subsets of AB, we take them and then just we add C to it, right? Always.
yeah, sure.
So that is the way we create. That is what is being said, right? And then you can also do this by mapping each subset to a binary number. That is the second approach, right? You take a binary number and then you,
Bits.
right, right.
Yeah, yeah, yeah,
Yeah, but provided then we'll have to be careful if what language you are implementing and how much number of set we have. Because if we take C++, if it's integer and unsigned, we can go more than 32-bit, right?
yeah, yeah, yeah.
So those things we'll have to take care. That's the only thing. Okay, so the normal approach will be like this one, right?
Yeah, this is the bits one, and this is the low. Below is the recursive one.
Yeah, let's go with the recursive one.
Yeah, yeah, yeah.
Okay.
So here I'm what you say? I'm calling the function DFS function, that recursion. I'm passing the array, the empty list, and the resultant array in which I'll be storing the subset. So initially empty array will be appended to it. Now what will happen? So is like zeroth index. So it will first one will be added to your what you say, the list, and remaining the recursion will go on 2 and 3, right?
Mm-hmm.
And subsequently 2 will be added and 3 will be left alone, and again 1, 2, 3, and we'll keep on iterating like that.
Okay.
Yeah.
So, well, the slight difference in what has been in its implementation in the book, Okay. If we just follow exactly the way it is said, right? The way it is like you create a helper function and you pass all that array or whatever it is along with the index, right?
Yeah.
Okay. So then, okay, you are also almost doing the same, right? Yeah.
Yeah, exactly.
Yeah.
And passing on the remaining of the
Right.
DFA.
And then for the base case, you are just putting empty one first, because if your size is 0, right?
Yeah, yeah.
And then actually when you come to the other part, when we have the size not 0, you actually start getting all the subsets of the previous one
And appending.
and append it, right? Yeah.
Yeah.
Yeah, that is what also is in the book, right? Yeah. But only
Yeah.
your Python implementation is slightly different, which I'm trying to understand it. Yeah.
Okay, sure. And this is the bits one, lava one.
Okay.
Like
So
yeah. So here just what I'm generating all the possible 8 bits, right? I mean 0 to 8 because three are there. So mask I'm creating 0, 0, 1. And again you can say, oh, sorry, this is 1. Then it will be 0, 1, 0, right? 0, 1, 0, 0. Now corresponding to this one, this what you'll have an empty set. And since 1 is set here, so you'll have 3. 1, 2, 3. If it is 3 will be set at the lab because this bit is set. Here you'll have 2. And again then what to say 2. Now 3 with what will have 0, 1, 1. So it will have 2, comma 3. And so on. Like again 4 coming to 4, what will have 1, 0, 0. So it will give 4. 4 not 1. First bit it will give, right? Because that is set. And again 1, 0, 1 if you take, so it will keep 1 and 3. And 1, 0, 1 it's done. After that 7, 1, 1, 1. So it will have 1, 2 and 3. And it's done, right? Somewhere missing 0, 1, 2, 3,
yeah,
4, oh, 6, 6 I'm missing. 0, 1, sorry, 1, 1, 0. Actually it should have come earlier.
Yeah. So we just look for if the bit is set, and then we add that particular element in our subset, right?
Exactly. Yeah. So I'm just, this is 2 raised to the power like n, like 8 bits it will generate. 8 such numbers it will generate. And going through the number and just going through the bits. So I'm just checking whether the bit is set or not. If it is set, like I'm checking whether which one is set. If it is set, corresponding to that bit, I'll pick the number and append it to my result. Yeah.
That's good. And also for this problem before, what said, like in the implementation, how can you actually get the time complexity, and the space complexity?
Okay.
So what is said, like each and every element will either be present in the subset or not, right? So that will be
Yeah.
two choices.
Two possibilities.
Two possibilities, right? So therefore each element will have two possibilities. So if there are n elements, it will be 2 multiplied by 2 multiplied by n times.
2 raised to the power n, yeah.
Yeah, it will be 2 raised to the power n. And then, so that is the space complexity. So if we have to go for the time complexity, we still have to go for each and every element, right?
Yeah.
Yeah. So, but it's said like if we have n elements, each element can be only half of the sets in half of the subsets, right? So therefore, the time complexity will be like n multiplied by 2 raised to n minus 1, right? And so therefore, the space complexity big O of n will be n into 2 raised to n. So that is what the correlations that has been mentioned. I think that is reasonable, right?
You mean the time complexity is 2 to the power n, right? Which is basically exponential, right?
Yeah, it should be because either element can come or it cannot come, right?
Correct.
Yeah.
And the space complexity, how much it will be? Because we are going on the recursion path, but we are unwinding, right?
Yeah, so it's
it is 2 raised to n.
2 raised to the power n, you can say. Yeah.
Okay. But I think we may not be keeping all the elements on the recursion, isn't it? It will be maximum the
length
depth.
of the
Yeah, it will be the height of the tree, and then we are coming to the other part and then unwinding and setting the other inputs, right?
Yeah,
So
but actually we are creating subsets. So that is what the is
oh, okay. You mean
complexity.
to say that including the not only the stack space but also the not on the recursion one. Sorry, not on the bit one because there is no stack space, but on the recurs. Okay, so here basically whatever the result also we are also thinking to be part of the response, right? That's what you mean.
Yeah, that
Okay.
that looks very different because usually we don't take it,
Yeah,
right? We don't
correct.
consider. Yeah, absolutely, you're right. Yeah, I never thought about this, but it's a good point. But as that is what is said, because I think so the call stack space is very less. It's almost
In the bit,
not.
actually, it is of one basically, right?
Hmm,
Because there is no space. Input array, we are just picking those and building the response.
hmm.
So
So if
implicit stack we are using now for that.
for the recursion, right? Not
Yeah,
for
yeah, yeah.
the bit one in the
Okay.
seven, not but for the recursion, yes, that will be the depth of the tree, right? How much we are going deep, and anyway, we are unwinding after reaching to the last bit, right?
Hmm.
So it should be order of n, right? Worst case, like if the tree goes straight, I mean, entire length of
May
n
not
will
be
push.
always right, Susan, because in this case, we know to choose or not to choose, right?
Correct.
Yeah. So what
Because
would you say then in that
it
case?
would be the think about this way, right? We are you are so the height of the tree is actually correct. Yeah, so the height of the tree in this case will be number of elements. Yeah, you are right.
Number of elements. Yeah, yeah,
Correct.
yeah.
Yeah, because anyway we have to, let's say we choose first element, we choose second element, we choose third element, we choose fourth element, then we come back and unchoose the fourth element, right? Anyway
Hmm.
we have to
Yeah.
go to the fourth n level. Yeah, right.
Yeah, so that stack space actually is not so
Big.
bit of a concern, right? Yeah, that's
Yeah.
true.
Exactly.
Yeah.
Yeah.
But therefore, I think it said like if you would try to create a subsets, because subsets is a huge, the input size is also lesser, but the subsets will be more, right? So therefore, 2 raised to n, and it's more. So maybe it's good to actually talk about this in an interview, maybe.
Yeah. Yeah.
Yeah, even if we discard most of the time over the output, but here it makes sense.
It's in here we do n equal the length of the number. Is that kind of I think this kind of little optimization, right? Is instead of going to like 32 bit, and then we only look through the number of the length of the number only.
In bit approach, you're telling. In bits
Yeah, but
approach.
normally like we look through 32 bit, right, for the second for loop. But this
Mhm.
one we look through the length of the nums only, right?
Yes. Hmm.
So that little will optimize.
Yeah. So this is more space optimized bits one.
Right, right, right.
Yeah, but time
Yeah, but
complexity will take more, I think. N
hmm,
into number, n into what you said, 2 raised to the power n minus 1, whatever.
right.
Yeah.
So, but the reason why this has been included in our recursion chapter also, because it's a DP, sort of DP, right?
Yeah.
So I look at that way. Maybe it's a bottom-up approach, and this is the most efficient one, right, to do
Which one? Bits one you are telling
the
or
bits one, yeah.
bits one? Yeah. And DP, and we are not doing any kind of memoization also, right?
Yeah.
But
Just thinking.
DP we are saying just because recursion is there, so
Yeah, it's a
It
recursion
will be
chapter,
backtracking
recursion and dynamic
actually.
problem.
But
Yeah.
Santosh, in the like bitwise solution, I mean this counting bit solution, you are counting n times inside a loop. So the first loop is 2 raised to the power n times, and inside every time you are running it n times. So
yeah.
it is n dot 2 raised to power n. So I think it's not runtime complexity is not good if you generate in this way. So I think the better runtime you receive if you generate in a recursive manner.
But there also the output will be the same, no?
Yeah, but here you are doing additional n times for every combination, for every subset. So this
But space,
is a
okay.
nested for loop, what I'm saying.
in the
Yeah, that.
7.
Yeah,
But
actually, okay. Mhm.
but
This
again, this will be fixed only, right? Constant 32-bit only, and will be right bit in the range.
no, this is n times. This is n is
Oh,
number
sorry.
of objects. I
Yeah,
mean, you
yeah,
can say, but you are doing it every time. That's what I'm saying.
exactly.
Well, you are saying it is n into 2 raised to n, correct?
Yeah.
N dot heart, yeah. This is what I'm
But
saying.
that is what actually is for the time complexity for the recursion also. Means at least as per the book.
Why?
I think it should be
Yeah, that's
2
Can
what
raised
you?
to the
it is.
power n for the subset one, right?
Yeah. It should be 2 raised to the power n only because you are generating them through the call stack. So this additional n factor is just compensated because you are saving it in the call stack.
Stack. Call
So
stack, yeah.
here, there you are not saving it anywhere. That's why you are paying additional cost every time.
But in white book, it is written like that.
Okay, if I read, I'll just read the sentence what is said, assuming that we are going to return a list of subsets, then our best case time is actually the total number of elements across all of those subsets.
Mm-hmm.
So there are 2 raised to n subsets, and each of the n elements will be contained in half of the subset. So which is 2 raised to n minus 1 subsets. Therefore, the total number of elements across all of those subsets is n into 2 raised to n minus 1. Then we will not be able to beat O of n into 2 raised to n in space or time complexity. So that is what is mentioned. So when we are doing a recursion,
Can you tell me page number, which page number you are referring? So it will be helpful.
it is
131.
I'm referring to 360. I'm going through the solution
Okay.
on 360 page.
360. Okay, I was just this is what I
Yeah,
felt
absolutely.
because it's an
What you
inner
said,
loop
that also
and
came to my mind. Yeah, exactly.
yeah. So
when you are collecting the result in recursion, you're going through that many number of bits, right? Or that many number of characters to collect in the array, the output array. That's why it's n2 raised to n in recursion.
Yeah, that is what it exactly mentioned there.
No,
Correct.
why we need to go? It is just append, right? Every time.
Yeah, so think of append. Append is also like you're appending. What are you appending and how, what? So that also takes time, right?
It's a
Copying
constant
kind of.
operation, right? Ending, isn't it?
No,
But
internally it will take off and only, right?
so
If
every
a big
operation
list
will
is there,
count.
big list if you are appending, then
No, normally if we like, I'm not sure in Python, like this return will be just any kind of object, right? So in this
yeah.
case, let's assume this is string. Okay, so string internally, not sure how Python, but in Java it's a character array, right? And
Okay.
appending to the end of the array is always a constant operation, right? Like you
Yeah,
just
that
know.
is also in Python, like appending item to the list of one.
Correct. So in
Yeah.
that case, the return dot append. So
So
basically
you're
the
saying,
path.
okay, so let's think about it. There is an empty list, okay, and now you're trying to append, say A to Z. You think like the append is just gonna be constant time? You're gonna be creating space, right?
Yeah.
How
Yeah,
is
I
that?
mean, we need to iterate over the source string,
Yeah.
but let's say that I'm iterating over A to G, then I take A, put it in the return string, then I iterate over B, then for B, I don't
Yeah.
have
So
to.
so that you are iterating over something to append.
You are creating, right? Actually, because you have to create a subset. Every
Yeah,
time when you append, you are just not appending. You are taking the previous subset.
yeah, exactly. And then
So you
appending.
are forming it, right? So then when you are actually creating it, so you are creating it from scratch. So therefore, it will be that will also count, right?
Mm, I believe here the path, right? The return is already will be different in the recursion stack, right? So whenever we first come, the return will be empty. Okay. So then, so the return dot append. So path is basically also empty, right? Then we just append the empty one. Then we go to the range, and then then we go to the numbers, and then path plus. Okay. and then we go to the return. So at this time, the return, so whatever the assumption is that the path is like whatever we are appending, we're always appending to the end, right? Because the path will be keep on changing.
Okay, this
So
is
I
an
think,
interesting thing. Yeah. Okay,
yeah.
let us just slightly go through this. I'll just annotate. We'll just take
Yeah.
a simple example. Okay, so we
What
have
is
like,
it?
yeah, A1, A2, and A3. Okay, so now this is the first one, empty one. Okay, so we created one. So now we are moving to the next one. So that is the A1, right?
Yeah.
So we create A1. Okay, now we go for A2. So we take both of them. Okay, so what I do is I take the first one. Okay, and I just add a A2 to it. So this is a new one I'm creating. When I take A1 and then append it, okay, so what I'm doing here, I'm taking this A1, but I'm creating this one right here. So
Copying and
this is
creating.
an
Just
additional creation. So this is also an operation, right? So if we keep on incrementing for more, like if I go for A3, then I take again, if I take maybe I'm
Right,
done with
right.
this.
Yeah,
Yeah.
yeah, yeah.
So this is
Yeah.
an
So
additional thing what we are doing. So
yeah,
that is
in
what she's
Python it
trying to
looks
say.
like
Yeah.
you know, but yes, because we have to return a array of array, right? Like a 2D array, correct?
Yeah. Yeah.
Ah, okay. Yeah, that makes sense actually. So
Yeah.
every time the number of elements we have to iterate, maybe 2 elements or in this case maximum 3 elements, but we are iterating those elements in the whatever that subset and creating a new one and then appending it.
Yeah.
by
Like
appending
2D
it.
array. Yeah, yeah.
Yeah, just one comment, right? Like whenever you call the recursive call again, effectively you are doing a path like the one that you have in hands, and then adding the next one, right? But if you see here, you are actually like, you know, you are creating a new list here, because this concatenation here in Python is going to read like every elements in path and then add the new one that is coming. One idea that we could do here, I think, like to better improve is like the fact that like instead of like appending this guy with this plus sign, right? We can actually just do append, like path dot append then nums of I, because then you don't go over O of n in this operation. This is gonna be O of 1, because in Python append is just like you know, appending in the last element of the array.
But at last, every time the element will be appended to the list.
I mean, that's what you like. The path plus nums y is actually concatenating to list. So you are going over all elements of path, and then finally, you know, adding this nums I here. So if you do like path dot append nums I, then that's O of 1.
Okay.
Yeah, that might be the case for Python, but
Yeah,
if you look at it for general way, like, you know, because I don't know, then there will be we'll have to discuss with the interview, but the general case might be like this, right? So that makes sense what's mentioned there. Right?
Yeah,
It becomes
first,
language agnostic append and all. Yeah.
before you append, you have to like kind of clone the existing set first,
Right.
right? And then you append to it.
Yep.
Because you every time you go into that recursion, you always double the set. And first, you know, think about it, to clone the existing one and append that character to the existing one.
Correct. Makes sense. Yeah, but that's a good one also about Flavio. You brought about Python, right? So that's a good thing to think about it, right? So
Yeah.
there are some ways which we can avoid this. Okay.
Yep.
Yeah. Good. Okay. So I think this is.
Yeah, sure.
Yeah.
Then
Okay, let's move. Then,
this magic and robot is there.
well, no. Actually, see, we have only few problems, right? So after
Okay.
power set, we go to the permutations with the duplicates one 8.7.
Okay, that's in the lead code repos. That duplicate permutations with duplicate. You're saying
Without duplicates.
without. Okay, I haven't
The
taken.
simpler one. You have not taken one?
No, I thought 8.13. What they are mentioning that I've taken. Okay, you can share it. No problem. I mean, it's in lead code also, right?
Right. It's in lead code also, yeah.
Yeah, let me open.
So do you want the number of lead code?
Yeah, sure. Share it.
It is 46.
Yeah, let me open that.
So it says write a method to compute all permutations of a string of unique characters. Yeah, till Shashank opens that, I'll just go through the problem statement. It says write a method to compute all permutations of a string of unique characters. And
We
so
covered this problem last time already, right?
yeah, last week.
Why we do it again?
No, this is the book, right? So we just go through the book.
Yeah, but that last time is also the book, in the book.
Well, okay, the last time problem was with the duplicates, and this is the without one. This is the basic problem.
I thought last time we do both. The first we do non-duplicate, and then the second we do duplicate.
Actually, this problem has been repeated in many sessions, so it might look that last.
No,
We can go once again.
what he's saying is makes sense, Leon, because when we were actually talking, I think Vishal was there, and Vishal also said like he showed us the other way, and then also we discussed about without duplicates also. Yeah,
Exactly.
yeah. But if I just read through the hints, okay, yeah, it's just like you can go through the problem statement.
Yeah, it's the same problem statement. Collection of distinct integers is given, and you have to return all the possible permutations of it.
Okay, so no problem. I'll just quickly go through the hints what said, because here the problem is of string and the lead code is giving as an integer. So there were two approaches what are said in the book. One is, suppose you had all permutations of A, B, C, how can you use that to get all permutations of A, B, C, D? Okay, almost the same what we did in the previous approach, right?
Yes. Yeah.
The previous about the superset. And then the permutations of ABC represents a way of ordering ABC. Now, how we want to create all ordering of ABCD, take a specific case of ABCD such as BDCA, and then you repeat. It's the same way, like you take one of the element, like in this case, if you are taking one, then the remaining ones are 2 and 3, then you actually order them in different ways, and then you prepend one to that. That is exactly what is said in the approach one. Okay. And then the second one is like if you had the second approach, if you had all permutations of 2 character strings, could you generate all permutations of 3 character substrings? And to generate a permutations of A, B, C, D, you need to pick an initial character. Okay, that was the second approach, what he said. Okay, the A, B, C, D, and then you permute the remaining characters. Okay, so I think the first one was different. Sorry about that. Yeah. Given a string such as BCA, you can create all permutations of ABCD that have ABC. Okay, so what is being said is just out of ABCD, you remove one of them. Okay, so you remove one of them, like and then by inserting D into each possible locations, right? Suppose if we have BCA and if we have D, we can insert D before BCA, that will become DBCA, or it will be inserted in BDCA, something like that. Okay, maybe I'll just share this one.
Sure.
Yeah. Okay, I just got this one also now. Instead of reading. Is it visible?
Oh, yeah.
Yeah. So this portion, right? What is saying here? Given a string BCA, we can create a permutations of ABCD that have ABC in the order of BCA by inserting D in like DBCA, then BDCA, and BCDA and BCAD, right? So we are just putting D at every location, each and every place, and then we are generating. That is the first approach. And the second approach is the way it is like you take A, B, C, or D out of it, okay, and then permute the remaining characters, and then you just prepend the one.
So in the second approach, like you select one option, like you pick any character, you go this way, but then you need to pop like when you're coming back from the stack, right? So then you can have another selection.
Right. So whatever selection you have, you just remove one element and then you do for the remaining. and then you prepend this.
Okay.
Yeah. So there are two approaches. Yeah.
Could you give an example of approach 2?
Okay. So approach 2. Well, let me annotate here then. Oh man, where is that annotated? Okay. So the approach 2, right? So if our means where we are coming from the recursive stack, right? If it was given the same thing, let's take if it is A, B, C, D, correct? Okay. So A, B, C, D, and then okay, and then what we do, we just remove. Okay, so let's take this one, B, C, A. Okay, and then we have D. So we
Yeah.
can insert D as first, like we can make D, B, C, A, and then we have B, D, C, A, correct? And then
BCAD.
we have B, C, D, A, and then we have B, C, A, D, right? So we can form this one. So next time we won't get B, C, A, but we can get something like A, C, B, right? The same thing
Yeah.
we do for D, okay? Then we have another one, same thing we do for D, okay? And then we keep it doing for all.
Yeah, that's approach 1, right? It's not approach 2.
This is 2 only. What is?
This is 2, this is
Mm.
2, and then approach, oh yeah, you are right, this is approach 1.
1. Yeah.
This is approach 1. For approach 2, it said like you take one of them, okay? They look almost similar, yeah.
If you add all permutations, yeah.
Yeah, you pick one of them, but in here we are inserting, right, D every time, but there we are prepending it, okay? So oh yeah, in the other approach you just take A, B, C, D, either of it, and so whatever we get, the remaining one, like if we have A, B, C, D, right? So we have removed A, so we have B, C, D, right? So we keep on, creating permutations of this, and just append A to that always. So A, B, C, D, then A will be C, B, D, and all that. So there we are prepending it, and here we are inserting it. So that is the only difference.
Yeah.
Inserting at different positions.
Yeah, for the option 2, right? Like I think the idea is like so start with, let's say, the basic one that you can think of, let's say A, B, C, D, right? So like you select, let's say, all of those available characters, right? So what you do next is, like, while you are, like, coming back from the recursive call, you are actually fixing the characters. So like if you have A, B, C, and D, you are saying, okay, now that I reached, let's say, position 2, like in the call stack, let's say A, B, and like what I need to do now is select C or D. So like if I go with C, the fourth one can only be D. But then when I'm coming back, I say, hey, I already selected the C as the third character, and let me now get the only one that is remaining between C and D, which is D. So now you bring A, B, and D, and the fourth one can only be C. You are always fixing, let's say, the amount of characters up that point, and then swapping the other ones.
Right,
Okay.
right. Yep.
So you're fixing character and then. Okay.
Yeah.
Yeah. So you fix up that point, and then the remaining ones you are always swapping.
Yep.
How will you swap like?
Swap in the sense like if you have A, B, so you fix it A, B, right? So your call stack is only B. So the remaining one is only C and D. So one option that you do is C and D, or the other option is D and C. So for the case of where you fix A, you can have B, C, and D, or C, D, and B, or D, B, and C, or so on for the second one. And then you keep doing this like stack by stack call.
Makes sense.
Yeah. So at least we know that there are two approaches, right? Because most of the time we think of only a single approach, but this gives a very clear idea. So there are two, and we can think it differently also.
Fix and swap the characters. Yes.
Correct. Yeah. So this is good. Do we want to go through the code for this, or? Yeah, you just entered, it seems. Yeah. Okay.
Cool.
So I
Yeah.
think it's like 8 minutes only for the next one.
Okay. Yeah, yeah, sure.
So do we can quickly go through the code.
Sure, sure.
Okay. Well, let me share the screen then. Okay. So this was the permutations one, right?
Yeah, exactly.
Well, I don't think I have that also. No, I don't have the ones what they have mentioned. Yeah. No, sorry, I didn't create that either.
Okay, no problem. Let's go through this only.
You have that?
Okay, yeah, I have. I mean, it's
Well,
like same pending and pending.
sure, go ahead then.
Yeah, sure. Let's see. I mean, I was talking about. So this one I have. Are you talking about this? Like I'm creating first what you say list of list as a resultant array in which I'll be storing, and going through each of the number and their indices in this array. So hereafter what I'm doing, I mean for each index, the j will run from 0 to that. Like if I equal to 2, from 0 to 2 it will run, and whatever the previous result we have, we are appending, I mean we are taking elements till this till jth character, appending that particular the current num to them, and then what do you say, the remaining from j onwards to the remaining, I'm passing it for I mean storing it in the new res function, and this will continue till what you say till this loop
Right.
till the j equal to 3. Yeah.
So this is the approach one, right? Yeah.
Yeah.
Okay, but you are not doing it the recursion way, right? So
No.
yeah.
If somebody has those.
Oh no, I also didn't do that. Maybe okay. Maybe next time we'll
Yeah, sure.
discuss about it. Right? Yeah. Okay. I think we are almost closer for the we won't be
Next
able
section.
to discuss the another problem, right?
Yeah.
So it will take more time. Anyway, but the paint fill problem